Hi, I'm Pierluigi Plebani, and with Claudio Di Ciccio and Giovanni Meroni, I would like to present our joint work concerning the pros and cons when considering blockchain to enable business process monitoring. We think that this analysis we performed and we have described in the paper could be useful to researchers and practitioners that really want to understand when blockchain can be an interesting platform to consider and when it is better to avoid. The outline of this presentation is quite simple and follows the title of the paper. First of all, I'm in charge of framing the problem we would like to investigate. There's to understand which are the main issues when considering the business process monitoring according to different standpoints. Then Claudio will give you a very short but meaningful introduction to blockchain needed to appreciate how the process monitoring can take advantage of blockchain. To this aim, a reference architecture will be proposed. Finally, Giovanni will consider the potentials of blockchain in terms of data immutability, trust, and distribution, and at the same time the drawbacks in terms of latency and cost with respect to the proposed reference architecture for process monitoring. To better frame the problem and to organize our analysis, we rely on a classical multi-party business process involving three actors: a manufacturer in charge of producing goods, a shipper which will deliver these goods, and the customer which will order and wait for those goods. A more formal representation of this example can be done using a BPMN collaboration diagram, in which it is possible to see the three internal processes corresponding to the activities performed by the three organizations and the interaction among them, which can involve data as well as physical artifacts. Given this multi-party business process, three questions are now considered. Why to monitor, how to monitor, and what to monitor. Why to monitor depends on the standpoint. I can be one of the actors, and in this case I'm interested to check if I'm behaving correctly and also performing well, thus checking deviation with respect to the model or analyzing the KPIs. Or I'm interested to see if the resources I'm managing are properly managed. Those resources could be internal ones, so I need to understand if they are properly utilized, or artifacts sent to me and for which I'm responsible during a portion of the process, so I need to inform about the status. Third, I can take the choreography perspective with the objective of checking if the other parties are behaving correctly, not only with respect to the control flow, but also with respect to other obligations. Moving to the second question, how to monitor, in the literature there are a lot of approaches which can be categorized according to this schema. For instance, conformance checking is able to check the deviation of the instances with respect to the model, or business activity monitoring is more focused on the internal activities. In most of the cases, event logs are fundamental as they represent a dataset which informs about the status of the activities or artifacts. This is strictly related to the third question, what to monitor, so what to store in the event logs. First of all, I could be interested on how the activity evolves with respect to their state machine. This can be done relying on the information provided by the operators in case of manual activities, or by the BPMS itself in case of automatic activities. Finally, by means of sensors, we can gather this information from the field. I could also need to collect information about the collaboration among the actors. So, how the activities are performed by all the actors, and here we need a third party, which also implies some privacy issues. Finally, I can take the choreography perspective, so I can only see exchange message and artifacts, so this can limit my visibility about what is happening inside the different actors.
A blockchain is a protocol, namely it's open for implementations. Let us see some of its general fundamental notions, so those that are useful to discuss how to monitor processes on blockchains. At the very core of blockchains, we have the concept of transaction. A transaction occurs when assets are sent from an account to another one. The sender digitally signs the request for the transfer, and upon the validation of the transaction, the recipient's account gets the transferred amount. A blockchain essentially consists of a collection of such transactions. The append-only list of ordered transactions is named ledger. A block collates segments of the ledger. To keep the original order of transactions within the ledger, every block refers back to its predecessor through hashing. This mechanism of hash links from a block to the previous one allows the history of transactions in the blockchain to be tamper-proof. As the ledger, and so the blockchain, are append-only lists, all transactions, as well as the information they bear, are meant to be permanently stored. To ensure that data are not lost if a system storing them crashes, data are replicated over the nodes of a network. Distributing the ledger makes for permanence, but it also entails that the nodes may not have the same notion of the blockchain status at every moment. Also, we do not have a real-time clock that is valid and the same for all the nodes. Nodes communicate among them to get their notion of the blockchain up to date, but also to keep their data locally safe. To validate the transactions and decide what is the next block to be published, we say mined, there are procedures learning locally to every node. Now, we won't enter into the details of communications, validations, and mining, but you see that maintaining such an infrastructure has a price. So Bitcoin, Ether, Ripple, and other cryptocurrencies were indeed devised to pay back the effort of the nodes maintaining the infrastructure. Who can be a part of this blockchain network? Well, public blockchains allow any node to download the protocol implementation. Private blockchains, instead, are more like an exclusive club in which access is restricted. The validation of transactions can be either allowed to all the members of the club, so all the nodes in the network, or granted only to those nodes that meet given predefined criteria. In the first case, we say the blockchain is permissionless, otherwise it's permissioned. Now you see that all combinations of permissioned or permissionless, public or private blockchains can take place. Ethereum and Bitcoin, for instance, are natively public and permissionless. Hyperledger Fabric is designed as a private permissioned one. The special feature of some of the newer, say, second-generation blockchains is that they allow for so-called smart contracts. In good essence, smart contracts are pieces of code. Think of them as sorts of Java classes, except they are deployed and executed only in the blockchain. In Ethereum, it is called Ethereum Virtual Machine. They react to calls and are stateful by nature. So they're not really like the real-world contracts, though they're named alike. And they are defined as smart just because they execute by a machine, allegedly a clever one. So how do smart contracts work? Well, smart contracts have their own account. Transactions to those accounts bear additional invocation data, say the parameters. The smart contract executes the invoked function then. But don't forget that the blockchain is distributed by nature, so this execution potentially happens locally to every node of the network. You see, this cannot be for free, right? To run the code, the sender has to add some additional incentive for it. In Ethereum, it's called gas. Last but not least, welcome the notion of Oracle. Smart contracts can only be invoked from the outside with externally owned accounts. But they cannot fetch any information from outside the blockchain, nor can they invoke any operation in the physical world. A programmable interface, let it be software or hardware, operating as a bridge between the on-chain and the off-chain world is called an oracle. After this quick overview, let's see how a potential architecture for a process monitoring platform that operates with blockchains can look like. On the top left corner of the diagram, we can see the input. The process status, namely that of the process instances and the ongoing activities, and the artifact status, namely that of the information objects handled or observed by the process instances. The produced output is the monitoring data. It can be a collection of event logs, aggregate information for process analysis, audit reports, so on. A portion of this output can be kept private. See, it is inside the BPMS monitoring system box, or made public outside that one below. Public information can be used to let other interested parties, say auditors, to check, for instance, the compliance of the process with certain constraints. when enriching the monitoring platform with a blockchain, the monitoring logic may be or should be actually encoded in smart contracts. Notice that smart contracts can act as an interface to other blockchain-enabled process monitoring systems. On the right. Oracles are meant to extend the smart contract accessibility to off-chain data, say real-world objects or other information stores. To conclude, we can keep this architecture in mind as a reference for the upcoming discussion in this presentation.
The last part of this presentation will focus on the challenges that the interplay with blockchain and process monitoring brings. The main challenges of the integration between blockchain and process monitoring are related to three main aspects: the definition of smart contracts, the usage of so-called oracles to provide external data, and the management of the monitoring data themselves. Additionally, each challenge may have an impact on the design rationale behind the monitoring solution, on the strategies required to overcome the lack of a capability identified by the challenge itself, and on how to ensure that trust is not broken. One of the challenges related to the smart contracts is the transparency of the monitoring logic and data. On the one hand, smart contracts formalize how the monitoring should be carried out by all participants, and this is undoubtedly an advantage. However, this also means that the data and process model must be shared by all the participants and, in case of a public blockchain, potentially with everybody. Therefore, care must be taken to provide all and only the information needed for monitoring without sharing any sensitive data. A second challenge is the observability. Although every participant to the blockchain potentially has access to the information inside it, it does not mean that the information can be easily retrieved. Like traditional programming languages, smart contracts do not make their internal variables accessible unless they are exposed by creating an ad hoc methods. Therefore, care must be taken when designing the smart contracts governing the process of monitoring data, if those data may be used by other applications. The third challenge on smart contracts is their lack of reactivity. Indeed, a smart contract cannot invoke services that are deployed outside the blockchain. Also, every action must be triggered from the outside, as a smart contract cannot independently perform an action. To solve this issue, an oracle must periodically trigger the smart contract or perform service invocations on its behalf. However, the introduction of oracles brings other challenges. Firstly, we need oracles whenever the expiration of a timer must be implemented on-chain. In fact, the blockchain does not have an internal clock. Time is managed by the nodes participating in the blockchain, which assigns a timestamp to the transactions and to the newly created block. This means that, although we can set timers with smart contracts, timer will not expire at the specified time, but whenever the associated smart contract is invoked. Thus, we need an oracle to periodically invoke the smart contract in order to simulate the ticking of time. Secondly, relying on a single entity to provide external data goes against the principle of decentralized trust, which represents the main strength of a blockchain. To overcome this issue, multiple oracles should be used. This way, even if an oracle gets compromised, by comparing its data with the ones provided by the other oracles, it is still possible to reach a consensus. Finally, the linkage between oracles and smart contracts is defined when the smart contract is deployed and it cannot be changed. This means that it is not possible to replace a compromised oracle once the monitoring takes place. Likewise, if new capabilities are introduced in an oracle, it is not possible for an already deployed smart contract to take advantage of them. Finally, there are also challenges related to the management of data. One of them, although not specific to blockchain, is the quality of the monitoring data. Indeed, the blockchain is often thought to be immune from poor quality data. In reality, this is only true for the data that originates from the blockchain itself, such as crypto coins. effects, as their creation and management is strictly controlled by the blockchain. However, when external data are introduced in the blockchain, their quality is not magically improved. Furthermore, some of the mechanisms that handle the assessment and improvement of data quality in traditional databases cannot be applied to the blockchain. For instance, poor quality data that are stored in the blockchain cannot be deleted or replaced with better data, as the blockchain works in an append-only fashion. Another challenge of data management is represented by the size of the data. In fact, storing large amounts of data in the blockchain has a high cost. For public blockchains, this cost is determined by the value of the crypto coins, but also for permissioned ones, there is a cost associated to the overhead caused by the platform, which becomes then inefficient. Therefore, care should be taken in determining which information must be stored on-chain and which can be left in other, more efficient kind of storages, such as a distributed file system. A third challenge is represented by the side effects that forks in the blockchain cause to the monitoring infrastructure. Indeed, most blockchains are prone to so-called soft forks, caused by two blocks being simultaneously mined. Such forks cause a lack of consistency in the monitoring information being collected. In addition, public blockchains are also prone to so-called hard forks, caused when the consensus protocol changes, which in turn can cause a split in the blockchain network and a potential service disruption. Before I conclude, I'd like you to take away from this presentation that the interplay between the blockchain and process monitoring is not straightforward. Although the blockchain allows to overcome some limitations of current process monitoring solutions, it also introduces new challenges that must be addressed. Such challenges can be framed in ones related to smart contracts, ones to Oracle, and ones to data management. Research in this direction is still at its infancy. However, once those issues will be addressed, blockchain will allow to build a solid monitoring platform. Thank you for your attention. Should you have any question, please feel free to contact us.